Alright, hello guys. This is Johnny, the organic tutor, and today we're going to start the first part of a series on alkene addition reactions. So this is part 1. Let's go ahead and get into it. So the basis of the alkene addition reaction is that we are going to have some alkene, so a double bonded carbon. Let's just say these are connected to hydrogens, so this is going to be ethylene. And it's important to remember that these two carbons here and here are sp2 hybridized carbons, meaning that they have 3 regions of electron density around them. This bond, this double bond, this bond, and this bond. So that is going to be our reactant, and then we're going to add something. And then we're going to form a alkane, so a single bonded molecule with something added onto it, and we'll see what that something is once we look at a few of these reactions. With an alkene addition reaction, to add something onto one of these carbons, let's say we just added X, that means we had to remove this double bond, so we had to remove the 2 electrons that made up that bond in order for this carbon not to violate the octet rule, meaning that carbon can't have more than 4 bonds. Alright, so in this first video, I'm just going to go over the first reaction in my list, and then we're going to go get into some of the other reactions. So in our first reaction, we are going to talk about a halide addition. And so what is a halide or a halogen? These are molecules like bromine, fluorine, chlorine, iodine. These are the elements directly left of the noble gases, meaning that they have 1 electron away from having that full outer shell that all atoms want. So this reaction, let's just say we have this molecule. Alright, so 2 double bonded carbons and then a single bonded carbon chain. I'll go ahead and write that out in the longer form. So this will have 1 hydrogen, this will have 2, and then this carbon will have 3 hydrogens. And then that is going to react with either, actually, let's use a different color, HCl or HBr. Alright, so there are a few questions we want to ask ourselves when we're talking about alkene addition reactions, or reactions in general. So the first question is what? So that as in what are we adding, since this is an addition reaction. So what are we going to add? Where are we going to add it? And how are we going to add it? And we'll answer these questions in just a sec. For now, let's focus on kind of the mechanism going on here. So we know that for HCl and HBr, we have 3 lone pairs on each. So this is going to act as the area of the reaction. This is kind of what's going to move the reaction forward, is this ability for the electrons here to move, as well as the electrons in this double bond. So let's just go ahead and use one of these as an example. Let's use HCl. Go ahead and write that out again. And then we have HCl. And let's use purple for our arrows. So the first step in this reaction is we are going to take, just remember that for each bond is made up of 2 electrons. Those 2 electrons form a bond that connect atoms. So we're going to take the 2 electrons from one of these bonds, from the double bond, and we are going to take that, and we are going to add that, or we're going to put that on the hydrogen. And when we do that, we also have to break the bond connecting the hydrogen to the chlorine. So we're going to take the 2 bonds from the 2 electrons from the bond for HCl and place those 2 electrons on the chlorine. So what does this do? Well, at first, let's just kind of know what our nucleophile and our electrophile is. So this is our nucleophile, and then what is our electrophile? This is our electrophile. So remember, negative attacks positive is kind of the simplest way to put it when you're kind of trying to understand nucleophiles and electrophiles. So this is how I always learned it. Negative attacks positive. And this is a nucleophilic center in this double bond that is able to donate those 2 electrons to that hydrogen. Alright, so once we do that, we're going to look at what intermediate we had formed. Let's go ahead and go back to white. So when we form that, obviously we're going to form a chlorine with 8 electrons, so 4 electron pairs, giving it a formal charge of -1. So that's one of our intermediate products. The more complicated of our intermediates, is going to be what happened over here. So when we break this double bond, what is that going to do? That is going to provide a positive charge on one of these carbons, and it is also going to attach the hydrogen to one of the other carbons, because again, what we see that this molecule attacked the hydrogen here, so that is going to form a bond. But which carbon is going to get the hydrogen and which carbon is going to get a positive charge, or a carbocation? So the rule of thumb for this reaction is that the carbocation forms on the most substituted carbon. Alright? So if we look here, which one of these is the most substituted carbon? That is going to be this carbon. You're just picking between the 2 carbons that are directly bonded by the double bond. So this one or this one. This one here has a substituent on it. This just the methyl group. So that means that is the most substituted carbon. So we have a carbon here, and that was connected to another carbon. I'll go ahead and draw the hydrogens in. And now, since we broke that double bond, we have a single bond connecting that. And we originally had 2 hydrogens. And then also that hydrogen from the HCl is going to bond to this one. and we also have another hydrogen here. So this carbon has 4 bonds. It has a neutral charge, but this carbon has 3 bonds. Formal charge, the valence electrons of carbon is 4, and so carbon has 4 valence electrons, and then it has 3 bonds. 4 minus 3 equals plus 1. So that's how we get that positive carbocation charge. And let's not forget that we still have this negatively charged chlorine ion floating around. And if you notice here, a negative and a positive altogether will have a net charge of 0, and that's always important to keep up with your charges. Here, we started out with a neutral molecule and a neutral molecule. So to keep that net charge is a very important thing that you have to consider here. So these are going to be our intermediate products. Later, we will talk about how this intermediate step is important regarding the position of the carbocation and its ability to change positions based on which one is most stable. Now, the reasoning for why we want the carbocation on this carbon as opposed to the other is just due to the stability of carbocations. So the stability of carbocations generally will look like this. A 2-degree carbocation, 1-degree carbocation. And there are some other more specific cases mixed in here, but we're just going to be talking about this general case. The carbocation is more stable on a higher degree carbon or a more substituted carbon. So that's why we're going to choose this carbon to put that on. All right, let me go ahead and redraw this one more time. So we have okay, and our carbocation, and then we have 3 hydrogens on this one, and then we have our chlorine. So what's going to happen here is our second step, and it is a very, very simple step. We're going to take 2 electrons, or a lone pair, from the chlorine, and it is going to be attracted to the positive carbocation. These 2 electrons are then going to form a bond to that carbon. So, let's see what we're left with. We will be left with the final product. Oops. Sorry. That looks like this. And then we have to add on our chlorine. So this is going to be our final product, meaning the major product, or the more stable product that we're going to form. So now we can look at our questions. So 1, what did we add? We added a Cl in this case, or works the same with bromine if you had HBr instead. 2, where did we add it? We added this to the most substituted carbon. And this is a rule known as Markovnikov's rule. And I'll talk about that in another video coming up. And how we can talk about a couple things here. So the first thing is that we want to talk about the fact, this is a very important thing, is that carbocation was formed. So the formation of a carbocation really is an important thing, because that, we'll talk about this later as well, that gives us the option for carbocation rearrangements. And I'll make a video on that later. So that's one of the ways it was formed. And it was also formed, this word, called racemically, or racemic. So this basically just means it has a mixture of stereochemistry. R/S, or the spin of it. So if we go back up, we notice right here. Right here. If with our carbocation intermediate, what hybridization of carbon do we have? So we have 3 regions of electron density, so that's an sp2. So an sp2 carbon, that has a trigonal planar geometry. So it basically just looks like this. And this is a flat shape, and these are all 180 degrees. This being said, whenever we come up to our final product right here, this is an sp4 molecule. I'm sorry, sp3 molecule, because it has 4 regions of electron density. So that means it is trigonal. Oh, I'm sorry. Tetrahedral. And this is not a flat shape. So this kind of looks like a pyramid, kind of like that, with something sticking up. This has to have 2 different types of bonds. It has to have one bond going away and one bond coming towards you, because it has this kind of 3D geometry. So this is the bond that's going away from you. This is the bond that's going towards you. These are the bonds that are in the plane. Whenever we have an sp3 molecule with 4 different groups, we have to designate the spin of the molecule, whether it's R or S. And this is done using, these wedges and these dash bonds. And I'll also make a video about that later on how we can do that. But because we are adding the chlorine to a trigonal planar molecule, there is no true direction that the chlorine is specifically going to come from. Since it is flat in the plane, it could come basically from either side and form either the R or the S, pushing one of these bonds away from you, or it can push that bond towards you. So whenever we have that situation, we call that a racemic bond, basically a mixture of the R and the S configurations. And we'll get more into the stereochemistry in a future video. the next few videos, I will be talking about a few other of the alkene addition reactions, 4 more in particular, and then after that, we'll talk about some of the alkane addition reactions. So thank you guys for watching. If you liked the video and if it was helpful, think about subscribing or giving it a like. I hope this helps you understand alkene additions, because they can kind of look a little crazy at first and kind of hard, but I wish you all the best in your studies, and that about wraps this up.